What if everything we see in the night sky, every star and galaxy, exists because of a tiny imperfection? In 1920, astronomers believed the Milky Way was the entire universe, a single, isolated island of stars. But in 1923, Edwin Hubble studied a fuzzy patch called Andromeda and realized it was much farther than anyone imagined. It wasn't a cloud in our galaxy. It was another galaxy entirely, nearly 1 million light years away. In a single observation, the universe expanded from one island of stars to an ocean filled with billions of them. Something changed that smooth early fog into the structured, beautiful universe we see today. That transformation follows directly from the laws of physics, especially gravity, combined with the exact conditions present at the beginning of the universe. But understanding how it happened requires asking a simple question that turns out to be extremely important. Was the early universe perfectly smooth? And if it was not, what did those imperfections mean for everything that followed? The answer to the first question is no. And the answer to the second question is everything. About 380,000 years after the Big Bang, the universe reached a turning point. Before this moment, it was filled with a hot plasma, a dense fog of free electrons and atomic nuclei moving at extreme speeds. Light could not travel freely through this environment because it constantly scattered off electrons, changing direction again and again. The universe was opaque, not because light was absorbed, but because it was continuously redirected. Nothing could move in a straight line for long. Then eventually the universe cooled. As temperatures dropped, electrons combined with nuclei to form neutral atoms, mostly hydrogen and helium. This process happened almost everywhere at the same time. And when it did, the universe suddenly became transparent. Light was finally able to travel freely. The photons that had been trapped began streaming across space in all directions. That light is still traveling today, stretched by cosmic expansion into microwave wavelengths. It fills the entire universe and can be detected as a faint glow coming from every direction. This is the cosmic microwave background, the oldest light we can observe, and it carries a snapshot of the universe at the moment it became transparent. At first glance, this snapshot looks almost perfectly uniform. No matter where you look, the temperature is nearly the same. The differences are incredibly small, less than 1 part in 100,000. For a long time, this uniformity was seen as a simple fact. The universe started smooth and structure somehow formed later. But when scientists measured that background more carefully, they found something hidden within that smoothness. There were tiny variations, small regions that were slightly warmer and slightly denser, others that were slightly cooler and less dense. These differences were incredibly small, but they were real, and they changed everything. Because those tiny fluctuations, those almost invisible imperfections, were the starting points for every structure in the universe. Every galaxy, including the Milky Way, traces its origin back to one of those small density variations. So does Andromeda. So does every galaxy ever observed. The question is no longer whether the universe had imperfections. The real question is how something so small became something so vast. And the answer begins with a force that never stops acting and never reverses direction: gravity. Gravity does not smooth things out. That idea goes against everyday experience, but it is essential to understand what happened next. When you pour water into a bowl, it levels out. When you drop sand, it spreads. Systems at human scales tend to become uniform over time. Gravity at cosmic scales does the opposite. It takes small differences and makes them bigger. A region that is slightly denser than its surroundings pulls matter toward it. As more matter flows in, the region becomes denser. As it becomes denser, its gravitational pull increases. That stronger pull draws in even more matter from a larger area. The process feeds on itself. There is no built-in limit and no need for an external push. Once it starts, it continues. In the early universe, gravity was not acting alone. There was something pushing back. Hot gas created pressure, resisting gravity's pull. For smaller fluctuations, pressure won, causing the universe to ring like a vast instrument. But calculations showed ordinary matter didn't have enough time to build galaxies as quickly as we observed them. Something was missing. In the 1970s, Vera Rubin found that stars far from the center were moving too fast, far faster than visible mass could explain. The only explanation Galaxies are surrounded by a vast halo of invisible matter that produces gravity but doesn't emit light. This is the secret of structure in our universe, the invisible pull of dark matter. This idea was not entirely new. Earlier observations of galaxy clusters had hinted at the same thing, but Rubin's work made it clear that this was not a small correction. It was a fundamental feature of the universe. Further evidence came from many directions. The bending of light by gravity, known as gravitational lensing, revealed mass distributions that matched this invisible component. The large-scale arrangement of galaxies only made sense when this unseen matter was included. Even the tiny fluctuations in the cosmic microwave background required it. Today, the best estimate is that about 85% of all matter in the universe is this invisible form known as dark matter. Ordinary matter, the atoms that make up stars, planets, and everything we can directly observe, accounts for only about 15%. The universe is mostly made of something we cannot see and still do not fully understand, but we do know how it behaves. And that behavior explains how galaxies formed. Dark matter does not interact with light. It does not feel radiation pressure. So while ordinary matter was being held back in the early universe, dark matter was already responding to gravity. It began collapsing earlier. The same tiny density fluctuations affected dark matter, but without resistance. It flowed toward denser regions and began forming structures long before ordinary matter could follow. By the time the universe became transparent, dark matter had already built the first gravitational frameworks. These structures are called dark matter halos. They are not visible directly. No telescope can detect them through light, but their gravitational effects are unmistakable. A dark matter halo is a large, roughly spherical concentration of matter, held together by gravity, extending far beyond the visible parts of a galaxy. The Milky Way sits inside one. So does every other large galaxy. These halos formed first, and they became the foundation upon which everything else was built. The formation of these dark matter halos did not happen all at once. It followed a pattern known as hierarchical growth. Smaller structures formed first because the smallest density fluctuations collapsed earlier under gravity. These small halos then merged with one another, combining into larger halos. Over time, larger halos merged again, building even bigger structures. Step by step, over billions of years, this process created the full range of halo sizes we observe today, from small systems to massive clusters containing thousands of galaxies. When ordinary matter began falling into gravitational wells created by dark matter, the universe was transformed. Without that head start, galaxies might never have formed. Inside these halos, gas collided and cooled, sinking deeper toward the center, a process called radiative cooling. Eventually, this dense gas ignited into the first stars. These giants were born in a universe of pure hydrogen and helium. Their short, violent lives ended in supernovae, scattering heavy elements that enriched the cosmos. From chaotic, irregular beginnings, the first galaxies emerged, merging and evolving into the structured universe we see today. Images from modern telescopes, especially the James Webb, show that early galaxies were more developed than expected, containing stars and complex structures, even when the universe was young. Over time, the rate of violent mergers slowed. As the universe expanded, galaxies had more space between them, allowing gas within halos to settle. As it cooled and lost energy, the gas conserved angular momentum, spinning faster as it moved inward and spreading out into a rotating disk. This is how spiral galaxies formed. The organized rotating structures we see today are the result of that gradual settling process. But galaxies don't grow without limits. Star formation is regulated. Without control, a galaxy would quickly consume all its fuel. That control comes from the stars themselves. Massive stars end in supernova explosions. This energy drives shock waves and galactic winds that carry gas away, reducing the material available for future star formation. The radiation from young stars and their stellar winds further limit collapse, resulting in the stable cosmic balance we observe today. More star formation leads to more feedback. More feedback reduces the gas supply. With less gas, star formation slows down. As it slows, feedback weakens. allowing gas to cool again and fall back in. This creates a cycle where the galaxy regulates itself over long periods of time. However, this mechanism works mainly in smaller and medium-sized galaxies. In the most massive galaxies, something much stronger is needed. At the center of nearly every large galaxy sits a supermassive black hole. These objects can contain millions or even billions of times the mass of the Sun. When gas falls toward them, it forms a rotating disk that heats up and releases huge amounts of energy. This energy can outshine the entire galaxy. When a black hole is actively feeding, it can drive powerful winds and jets that heat or expel gas across the galaxy and even into the surrounding halo. This process is known as active galactic nucleus feedback. It plays a critical role in shutting down star formation in large galaxies. Instead of slowly regulating the process, this feedback can stop it almost completely. The gas is either removed or kept too hot to collapse, leaving behind a galaxy filled with old stars and little new activity. This is why many large galaxies appear red and inactive today. So galaxies are not just shaped by gravity and cooling. They are controlled by powerful feedback processes that determine how long they can keep forming stars. And those processes ensure that galaxies do not simply grow forever, but evolve over time. Step back and look at a galaxy as a whole, and it becomes clear that it is not a simple object. A spiral galaxy like the Milky Way is a vast, rotating system containing hundreds of billions of stars, spread across tens of thousands of light years. Every star is moving, each following its own path under the combined gravitational influence of everything around it. Yet somehow all of these independent motions create a stable, organized structure. This stability is not obvious. You might expect that over time, gravitational interactions between stars would disrupt the system, scattering orbits and destroying the flat disk shape. But in reality, stars are so far apart that close encounters are extremely rare. Most stars will never come close enough to another star to significantly alter their paths. Because of this, the overall structure of the galaxy remains intact over billions of years. The spiral arms themselves are not fixed structures. They are patterns known as density waves moving through the disk. Stars and gas pass through these regions as they orbit the galaxy, much like cars moving through a traffic jam. The pattern persists even though the individual stars are constantly changing position. Gas behaves differently from stars in these regions. When gas enters a spiral arm, it gets compressed. This compression increases density and triggers star formation. That is why spiral arms appear bright and blue. They are filled with young, massive stars formed from recently compressed gas. But galaxies do not exist in isolation. They are constantly influenced by their surroundings. Over time, galaxies interact, collide, and merge. These mergers can dramatically reshape them. When two spiral galaxies collide, their ordered structures are disrupted. Gas clouds collide and trigger intense bursts of star formation while stars are scattered into new orbits. Eventually, the two systems merge into a single galaxy, often forming a large elliptical galaxy with little remaining gas and very little new star formation. On even larger scales, galaxies are not randomly distributed. They form a vast network known as the cosmic web. This structure consists of filaments, sheets, and nodes connected across enormous distances. Galaxies form and evolve along these filaments, flowing toward dense regions where clusters grow. Between these structures are vast empty regions called voids. The position of a galaxy within this cosmic web influences how it evolves. Some galaxies continue forming stars, while others are cut off from gas and slowly fade. Over time, more and more galaxies stop forming stars in a process called quenching. Looking further ahead, the expansion of the universe will continue to stretch this structure apart. Galaxies will become increasingly isolated, and the large-scale connections between them will disappear. In the end, galaxies are not permanent structures. They are the result of a long, ongoing process shaped by gravity, gas dynamics, feedback, and cosmic expansion. From tiny density fluctuations in the early universe to the vast structures we see today, every galaxy is part of a story still unfolding. And the reason they exist at all comes down to one simple fact. The universe was not perfectly smooth.